Welcome. This talk and poster is titled REMEDI, Corrective Transformation for Improved Neural Entropy Estimation. In information theoretic learning algorithms, we often need an estimate of the entropy for a probability distribution. For this talk, we will be considering continuous probability distributions in d-dimensional space. In other words, they have a probability density function. Then we can define the differential entropy as the expected value of the negative log density function. Classical methods for estimating this based on samples include KDE, KNN, and sample spacings methods. These have nice provable properties like consistency, but produce poor estimates in moderate dimensions. KDEs can be improved by increasing the model class, for example, going to Gaussian mixture models. A recent development in that direction is estimating entropy with GMMs with a gradient-based optimization of a cross-entropy loss. So this work shows empirically that the fundamental problem of KDE estimates also unfortunately carries over to such GMM estimates. We introduce a deep learning based correction called REMEDI and show good performance of this method in moderate dimensions. We also prove theoretically that it satisfies a desirable consistency property. Then we investigate its performance where it belongs, which is in the information bottleneck framework. Here is an illustration of how GMMs can fail in 8 dimensions. The entropy estimates here are given by the validation loss function, plotted as solid lines here. We see that adding more and more components in the GMMs only leads to overfitting, and the estimates can thus not pass a certain barrier. Our method of estimating the entropy uses weakly fitted base models, Q, that allows us to compute the likelihood. For example, this may be a normal distribution, a Gaussian mixture model, or a normalizing flow fitted to the data. The difference then between our desired quantity h of p and the cross entropy that we obtain from such a model is then given by the relative entropy between P and the base model Q. This relative entropy can be estimated using Donsker-Varadhan's formula, which looks as follows. It's as a premium over expectations, which has been used before in mutual information estimation. So a question is, can we use empirical estimates for this? How do we estimate over this family of continuous bounded functions into R? And can we obtain theoretical guarantees? These are answered in the positive. Here is the loss function we obtain with empirical estimates, which consists of a cross-entropy part and the Donsker-Varadhan part. So this minimization consists of 2 parts. First, minimizing L_knife, the cross-entropy term, and then minimizing LDV, which is the relative entropy term given by Donsker-Varadhan. The first term is titled L_knife, since we use knife as our base model. I now hand it over to the next author.
We apply REMEDI on entropy estimation task. So on the left, we have the REMEDI training curve. In the middle, we show the workings of this approach. The red dots here represent the samples from the data distribution. We overlay them with the contours from the knife-based distribution. Here, the green patches represent the correction applied by REMEDI, and the results in on the right, where we see we've been able to capture the true 2-moons dataset quite well. Next, we apply this approach for entropy estimation on 3 additional datasets. Here we apply REMEDI on 8-dimensional uniform ball, uniform cube, and a triangle dataset. In all the dataset, the true entropy is being represented by the green dashed line. And we can see in all the data set, the remedy is able to closely estimate the true entropy compared to the baseline naive approach. Next, we apply remedy in information bottleneck framework. Here we show results on 3 image classification dataset, MNIST, Cypher10, and ImageNet. And in all the dataset, we observe that remedy gives us competitive performance. And in most of these cases, we observe that remedy is actually better than the other approaches. Next, we show the workings of remedy on IB latent space. And here we show the experiments on MNIST. On the left, we have the encoder samples from the MNIST latent space. And we can clearly see the 10 classes in the latent space. In the middle, we have the naive contours. Here we see that naive is only being able to capture 3 of these 10 classes. On the right, we have the remedy contours. Here we see that remedy corrections actually worked in terms of capturing these 10 classes. Next, we show the generative capabilities of our approach. Here we show one approach which is based on rejection sampling. Rejection sampling is important when we have budget to draw many samples from the base distribution. Here in this plot on the left, we show we have drawn 10,000 samples from this proposal distribution. On the right, following the rule above, we only able to accept 2,000 or close to 2,000 of these samples. A more efficient way to draw samples is through Langevin diffusion. In Langevin diffusion, we solve the below stochastic differential equation for different values of this diffusion parameter denoted by beta. And we can clearly see that starting from a proposal distribution, we can draw samples from the data distribution quite well. This is all for this talk. Thank you for listening.